Okay, can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so in the last class, we have done some numerical problem, I think. Was it a numerical problem in the last class?
Yes, sir.
Yes, sir.
Okay, so now let us proceed further. So now I am starting with a new topic, that is specific heat at constant volume. Okay, so this you know already also. See, specific heat is already known to you. It is the amount of the heat required to raise the temperature of a unit mass of a substance through 1 degree Celsius or Kelvin, whatever units you are considering. And when we consider this value at constant volume, means when this heat is supplied at constant volume, then the specific heat is actually specific heat at constant volume actually, and it is denoted by CV. So let us try to see what is the value of the heat transfer when the volume is constant. If there is a process in which volume is constant, the heat transfer is given by mCv T2 minus T1, and this is also equal to U2 minus U1, that is change in internal energy. And it is so because in case of a constant volume process, the value of work transfer is equal to 0. And you know from the formula of first law of thermodynamics, delta Q is equal to du plus delta W. So this is equal to 0. So it means delta Q is equal to du. And the value of du is given by mCv dt. This is valid for all ideal gases or all substances. Okay, so this is valid. And if I take it on it on a unit mass basis, I can remove this mass value here, and then it becomes the specific change in internal energy. So du, this is small, this is the small u, and this is the capital U. Capital U, when it is there, we have to consider the m also. So from this particular equation, you can see I can always say that the value of CV is equal to du divided by dt. So this is the value of CV. CV is equal to del U by del T at constant volume. Why I am taking partial differentiation is, you know, partial differentiation is taken when you are considering certain other parameter as constant. So that is why this volume is taken as constant here. So this is the value of the CV. CV is equal to del U by del T at constant volume. Now let us see. U is U is a property, T is a property, V is a property. Therefore, CV is also a property, because if you see the definition of CV, CV is equal to del U by del T at constant volume. So U is a property, T is a property, V is a property. That is why CV is also a property. Okay. Now, when I multiply this CV, what is CV? CV is the specific heat at constant volume. And what is its unit? It is kilojoules per kg Kelvin or joules per kg Kelvin. So that means the kg is coming out in uh, denominator. So when we multiply by mass and CV, then this becomes capital CV, and it is actually known as heat capacity of the system at constant volume, and the unit will be joule per Kelvin or kilojoule per Kelvin, depending upon the unit of the specific heat at constant volume. Okay, so quite simple, not very difficult. So it's CV is equal to M into CV. So this is small and this is capital. That is the difference basically. So this becomes extensive and this becomes intensive. Now we can talk about another term, that is enthalpy. So one is enthalpy, which is denoted by capital H, and another is specific enthalpy, which is denoted by small h. So how do we define specific enthalpy? As such, there is no definition for the enthalpy, but we define it as small h is equal to U plus PV. This is the product of pressure and volume. Okay, and it is an intensive property. When I am considering small h, it is basically intensive property because its unit will be equal to kilojoules per kg. Okay, because this is small u, and small u have the units kilojoules per kg, and small u is nothing but specific internal energy. And if I take capital H, it will be equal to m into h, and it will be equal to m into small u plus p into v. And this v is specific volume. Mind it, it is specific volume. So when I say specific volume, the unit of specific volume is meter cube per kg. So when we multiply this quantity, which is small h, which has the units kilojoules per kg, and the mass has the unit kg. So kg and kg cancels out, and the unit of enthalpy comes out to be kilojoules. So it is now enthalpy, not specific enthalpy, whereas this small h is specific enthalpy. So you see, I have done it here also. And then it can also be written as, when we multiply m and u, it becomes capital U, and when I multiply m to p into v is specific volume. So you should know that capital V is equal to m into small v. Okay, so that is how we get the value of capital H, which is equal to capital U plus p into v. So this is the total enthalpy, or enthalpy only. Now if you see here, H is equal to U plus PV, and U is given as CV into T, whereas PV is equal to RT. And this PV is equal to RT from the gas equation, because we know that PV is equal to MRT. And when I write PV by M, it is equal to RT. And I have just said that from this particular equation, I can always say that V by M is equal to small v. So I can write PV is equal to RT. So once I get this value, you can see that H is a function of temperature. You see the right hand side, in the first term the temperature is there, in the second term the temperature is there. So H is a function of temperature. So always remember that for ideal gases, for ideal gas, H is a function of temperature. This will not hold good when it is a real gas actually. So but in your course there is no real gas analysis, so you need not to worry much. Now we can discuss about specific heat at constant pressure. So what I have written here is, once again, small h is equal to U plus PV. Okay, U plus PV. And from the first law of thermodynamics, I know I can write this equation, delta Q is equal to dU plus PdV. So if I want to calculate the value of delta Q for a constant pressure process, so you can see I have put here small p. So it means it is delta Q for a constant pressure process. And this value we have already calculated, and this is equal to Cp dt. So in place of this delta Q, what I have done, I have put du plus pdv. Du plus pdv is equal to Cp dt. Okay. Now what we do is, this is for the time being, you focus on this equation, and now you start focusing here how what we have done here actually. H is equal to U plus PV, and when we differentiate, we have dH is equal to du, and first term on the, for when we integrate PV, one we will get PdV and other we will get VdP, considering in one case we are considering pressure as constant, in second case we are considering volume as constant. So dH is equal to du plus pdv plus vdp. But we are considering which process? We are considering pressure as constant. So this term will go, this goes. Okay, so we are left with du plus pdv is equal to dH. So this is the equation, du plus pdv is equal to dH. And from this particular equation which is written here, if I say this is equation number 1 and this is equation number 2, just compare both these equations. So you can say that du plus pdv is equal to Cp dt. Okay, from equation number 1, du plus pdv is equal to Cp dt. So this is what I have put here. And du plus pdv, one you can consider this part, this equation, and another you can consider this equation. So dH is equal to Cp dt. So from here we can calculate the value of Cp, which comes out to be del H by del T, at constant pressure. So Cp is basically uh, partial differentiation of enthalpy divided by partial differentiation of temperature divided by at constant pressure actually. So that is the definition of Cp. So we can say once again Cp is a function of temperature only, since H, T and P are the properties. Okay. So we can also say that Cp is also a property. Cp is a property. Okay. And why we say that Cp is a function of T? You can see here that C H mm, Cp dt. Okay, H is equal to U plus PV. If you see this particular equation, and from this particular equation, because we have just defined that dH is equal to Cp dt. Okay, so here I can write H is equal to Cpt, which is equal to or rather yeah, this U will be equal to CVT plus PV. PV is equal to RT. So if you see this particular Cp is also in some way a function of temperature only. Okay, and then here we have calculated Cp, capital Cp is equal to m into small cp. So this is the heat capacity at constant pressure, and we have discussed about the heat capacity at constant volume also. Now let us talk about the energy of an isolated system. Now energy of an isolated system, you know about the isolated system. An isolated system is one in which there is no interaction of the system with the surroundings. So that means the value of heat transfer and W work transfer, that is equal to zero. This is zero actually. And this is the first law of thermodynamics. If I say that this isolated system is undergoing a process, so I can apply this particular equation. This particular equation I can apply. And then, because it's a isolated system, this value will be delta Q will be equal to zero. This will become zero. This will become zero. So the value of dE will come out to be zero. And when we will integrate this particular equation, you will see that energy of the system will remain constant. So that is why we say that energy of an isolated system is always constant. So basically, what is an isolated system? In which the value of W is equal to zero, uh, Q is equal to zero, and then when we take these two values, the zero, then the total energy of the isolated system remains constant. Now let us talk about perpetual motion machine of first kind. Now what is this perpetual motion machine of first kind? Now this is basically a corollary of first law of thermodynamics, which you have studied in this chapter. Now what we are considering here is we have a engine here. Okay, we have a engine, and all of you are familiar with the engine. When I say engine, the first thing that comes to your mind is if you are driving any vehicle, then it has a engine actually. So engine is a device which is capable of producing work actually. Okay, which is capable of producing work if we are giving certain amount of energy to it. Okay, suppose we supply some heat energy to an engine, then it converts that heat energy into work. So we are considering an engine here, and we say that it is giving us some work W, and this is shown by arrow which have dotted lines, and we say that the energy which we are inputting into it in the form of heat is equal to zero. So this becomes a PMM1 actually. It is basically, you can say, a perpetual motion machine of first kind. Why it is a perpetual motion machine? Because what is happening in this particular case is that we are supplying zero energy. We are supplying zero energy to the engine, but still it is giving certain finite value of the work to us. Some finite value of work is given to us. Let us say 2 kilowatt. Okay, it is giving to us. So how you can expect any engine to give us work output when we are not supplying any form of energy to it? So it's impossible. So that is why we call that it is a sort of perpetual motion machine which does not exist. It is a sort of fictitious machine. Okay. So this is what is written here in this particular few lines. You can read it. The first law states that general principle of conservation of energy. So basically, first law is principle of conservation of energy. Energy is neither created nor destroyed, but only gets transformed from one form to another. Means we can convert heat energy into work into say kinetic or mechanical energy, potential energy, or say light energy, or something else, or electrical energy. Then it says there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. So this is what is happening in this particular case. What is happening? There is no form of energy which is disappearing. Okay, no energy is disappearing, but we are getting mechanical work continuously in this machine, in this particular machine. So it is not possible. So such a fictitious machine is called perpetual motion machine of first kind, or in brief PMM1, and it is impossible to have such a machine. Okay, this is one way of depicting this PMM1. Another way of depicting PMM1 is the converse of PMM1. Now, what is converse of PMM1? You can see it here. What we are doing, we have a machine here, we have a machine here, and we are supplying some finite work to it. Okay, we are supplying some finite work to it, and this Q which we are getting is actually zero. So what actually is happening? This machine is eating away all the work, but no other form of energy is actually coming out from the machine. Q doesn't mean that it is only heat transfer. There could be other forms of the energy also. When a machine is eating energy, mechanical energy or work, then some other form of energy must appear as per the first law of thermodynamics. That is not happening in this particular case also. So this is the converse of the above machine which is shown here, PMM1, and this is the converse actually. So what is written here? The converse of our statement is also true, that there can be no machine which would continuously consume work without some other form of energy appearing simultaneously. Okay, so some other form of energy must appear actually, and that is not happening in this particular case. Now let us once again focus on this PMM1. I would like to tell you one important thing about it is, see, if you focus on this engine, what is the energy which we are inputting? This is sorry, this Q we are inputting, this is the input energy, and the value is actually equal to 0, and we are getting some finite value of W. So what is the efficiency of this engine actually? The efficiency of this engine will be given by work output, which is W in this case, and the heat energy which we are inputting into it, W by Q. So this is work and this is heat. So this is the input and this is the output. So what will be the value of the efficiency of the heat engine now? The efficiency of this engine is equal to W divided by 0. So it will be approaching infinity, and no machine can have efficiency which is infinite. Rather, if you think about yourself also, uh, we are also not PMM1, because we eat food, and whatever is the energy that we are getting from the food, we are only able to convert very less amount of that food energy into work actually. Most of the energy is wasted in our body, and you know about it. Okay, so we follow the first law of thermodynamics. Okay, now what is the limitation of the first law of thermodynamics? This is very, very important. So first of all, the first two statements, if you see, the first law deals with the amount of the energy of the various forms transferred between the system and its surroundings. So it deals with what? Energy of various forms. Which various forms? Basically W and Q, transferred between the system and its surroundings. So we know that if it is a uh, thermodynamic system, so it interacts with its surroundings with the help of W and Q. Okay, so it could be W which is going out of the system or going coming into the system, and same way it is Q, and it is interacting with what? It is interacting with surroundings. Okay, with changes in the energy stored in the system. So naturally, if there is interaction with the surroundings, and we have both W and Q simultaneously appearing, so naturally, if there is some energy, so that energy will be either stored here or will be reducing within the system. And this is the same thing which is I have already told you. You can see it here. It treats work and heat interaction as equivalent forms of energy in transit. So it says that work and heat both are equivalent forms of energy. Okay, is it so? Is it so? This is a question for you people. Are heat and works equivalent forms of energy? Anyone?
Yes, sir. Both are energy in transition.
Both are energy in transition, but are they equivalent to one another?
Sir, one is due to temperature difference and one is independent of temperature.
No, that's true. See, are they equivalent forms of energy? No, they are not equivalent forms of energy. That I will tell you why. Because if you have, say, suppose you have any engine, you talk about automobile engines. Okay, so in that engine, what happens when you supply, say, 100 kilojoules of energy? Okay, so what is the amount of the work that you will get? The efficiency of the engine is only 40%, so you will get only 40 kilojoules. Okay, rest 60 kilojoules will be lost to the surroundings. Okay, if you drive a bike, there is a tailpipe, exhaust pipe, and if you touch that exhaust pipe, it's quite hot, and basically its temperature may be around 100 or 200 degrees Celsius. So it's very hot, so it's losing heat to the surroundings actually. So that is why you cannot say that both are equivalent forms actually. Heat and work are not equivalent forms of energy, but first law says that work and heat, they are equivalent forms of energy. Rather, they are not equivalent forms of energy. And then what does first law says? It does not indicate the possibility of a spontaneous process proceeding in a certain direction. Means it will not tell you that in which direction the process will take place. It rather says that heat and work are mutually convertible into one another. Okay, it doesn't tell us that in which direction the process should occur. For example, I give you an example. Suppose you have a cup of tea. Okay, you have a cup of tea. You have hot tea kept in the cup here, and the temperature is, let us say, 50 degrees Celsius, and you are enjoying the tea, and outside temperature is, let us say, 30 degrees Celsius. And suppose if you don't take tea, after certain period of time, you will see that the temperature will be reduced to 30 degrees Celsius, and it would be equal to the surrounding temperature. Now take another scenario. Now you once again have the tea, and now it is at 30 degree, which is available to you. Now tea is at 30 degrees Celsius. Outside temperature is also 30 degrees Celsius. Means the ambient temperature is 30 degrees Celsius. Now, can we extract heat and give from the surroundings to this cup of tea so that its temperature rises from 30 to 50 degrees Celsius? Because in the previous process, you have given the heat energy from the tea to the surroundings. ओके, अभी जो है हमने चाय में से कुछ एनर्जी 50 से निकाल के सराउंडिंग को दी, तो चाय का टेम्परेचर 30 डिग्री सेल्सियस हो गया. तो क्या अब ऐसा नहीं हो सकता कि जो सराउंडिंग एयर है या एम्बियंट है, उससे जो है 30 डिग्री से हम कुछ हीट ले लें और चाय के कप में डाल दें और उसका टेम्परेचर 50 डिग्री हो जाए? नो, इट कैन नॉट हैपन. यू नो इट. ओके, सो देयर इज a direction for every process. Okay, so all spontaneous processes occur from, you can say, what do you call, it's the concept of the driving potential. So where the potential is high, the flow will take place towards the lower potential actually. For example, in a electrical circuit, the electrical current will flow towards the lower potential. Okay, the water always flows downhill. It doesn't flows upstream on the towards the hill. So the processes do occur in a particular direction, and this is not given by the first law of thermodynamics. It only says that heat and work are mutually convertible into one another. So that is the basically deficiency of the first law of thermodynamics, or limitation of first law of thermodynamics. So what is written here? It is the, you see it here. Uh, it is the second law of thermodynamics, which assigns a quality to different forms of the energy and also indicates the direction, if any, direction of any spontaneous process. So it is only the second law of thermodynamics which will tell us in which direction the process will take place. Okay. Okay, so we have done some numerical problems. This is one of the numerical problems, very simple. I am not going to discuss it here, so I am leaving it for you to go through when you see the video actually. Okay, very simple. Yes, this is a good question, so I will go for it. This is an example from PK Nag's book. So let us read it. When a system is taken from state A to state B, as shown in figure 4.2. So this is state A, this is state B. Along the path ACB. So which is the path ACB? This is A C B. So this is the path we are following. 84 kilojoule of heat flow into the system. So this is the value which is given to us. QACB is 84 kilojoules. And system does, one more thing, because heat flows into the system. So if this is the system, and Q is entering into the system, so it is bound to be positive. Okay, as per the sign convention. And system does 32 kilojoule of work. So that means this is the work which we are getting during this process, which is equal to 32. And once again, when the work is done by the system, it is bound to be positive. So this is also given here. WACB is equal to 32 kilojoules. So these two values are given to us. Now if you see it here, now what I can do is, if you see, this is a process from A, C, B. So it is starting from particular point number A, passing from point number C, and then ending at B. And I know the values of heat transfer as well as work transfer during this process. So I can always calculate the change in internal energy during this process. And that change in internal energy during the process will be given by the first law of thermodynamics for a process. This is FLT for the process. Okay, for the process. And it is nothing but it is equal to delta Q is equal to du plus delta W, and it has been integrated from A to B. Okay, both the sides. So you will get this particular equation. You can see it here. QACB is equal to UB minus UA plus WACB. Okay. We, while calculating change in internal energy, we don't need to talk about point number C, because internal energy is a property. Okay, internal energy is a property. So we are worried about the initial state and the final state actually. So we rather focus on initial state and the final state. Okay, so from this particular equation we can calculate the value of UB minus UA first of all. So it comes out to be 52 kilojoules. Okay, so this is one thing. Now what exactly it is asking us to calculate, let us see that. So we have calculated the value of change in internal energy, which is equal to UB minus UA. Okay. Now it asks how much will the heat that flows into the system along the path ADB be if the work done is 10.5 kilojoule. Now it is asking about this particular path, the other path actually. It is talking about this path. That means this is point number A. You go along this path go up to point number D, and from then point number D, you go up to point number B. Now, actually, whether you follow the path A, C, B, or whether you follow the path A, D, B, okay, see, there won't be any difference in the change in internal energy, because in both the cases, it will be given by UB minus UA. And it is asking us to calculate the value of the heat transfer during this particular process. How much it would be if the work done is 10.5 kilojoules. You can see in the question here where I am highlighting here. So during this particular process, WADB, this value is given as 10.5 kilojoules. And once again, it is a process only. So I can use this particular equation, delta Q is equal to du plus delta W for the process ADB. ADB के लिए यूज कर लिया इसको, तो अब ये इक्वेशन लिख लेंगे हम, UADB is equal to UB minus UA plus WADB. Now you know this value is already given to us as 10.5, and this UB minus UA we have already calculated, it is equal to 52. So heat transfer comes out to be 62.5 for this particular process, which is taking place from A, D to B for this particular process. Okay, so we have calculated the part A, and we know now that the heat transfer during the process ADB is equal to 62.5 kilojoules. Now let us go to part B. Now what is part B? When the system is returned from B to A along the curved path. Now this is the curved path, this one. So it is, the system is returning back to the point number A. It comes back to point number A. Okay. So it is not saying whether you have gone from A to B or whether you have gone from A to B along the different paths. It is now talking about point number B. This is the starting point and this is the ending point. Okay. The work done on the system is 21 kilojoules. Now, work done on the system is 21 kilojoules. So this value of W B to A is not 21, rather minus 21 kilojoules, because it is work done on the system. So you know from the sign convention, if W enters into the system, it is bound to be negative. So we have to consider it as negative. And we have already calculated the value of UB minus UA as 52. As you can see in the previous case, it was here, यहाँ पे ये हमने 52 कैलकुलेट किया था यहाँ पे, तो हमारे पास इसकी वैल्यू ऑलरेडी है. So this is already with us. So now what it is asking, it is saying that does the system absorb or liberate heat, and how much of the heat is absorbed or liberated. So this is what it is asking, कि you have to calculate the value of heat transfer for this particular process. So you can apply this once again, this equation, which is the first law equation for this particular process. You know the value of WBA, which is minus 21. UA minus UB. Now, because the process is starting from point number B and ending at A, so I will be taking UB minus UA. UA minus UB. Okay. So the value will now be equal to minus 52, because UB minus UA is 52. So UA minus UB will be minus 52. So it is minus 73 kilojoules. So it means heat is leaving the system. So Q B to A will be equal to minus 73 kilojoules. So heat is going out of the system. Now let us see the part number C. If UA is equal to 0 and UD is equal to 42, okay, UA, this value is 0 and UD is 42. This is given to us. So find the heat absorbed in the process AD and DB. तो हमें इस process में AD and DB, we have to calculate the value of Q in both these cases. Okay. Now let us see what has been, how it has been solved actually. Now if you see, if you see the initial question for the process ADB, you can see it here. For the process ADB, the value of work was given to us as 10.5. Okay, so this is already known to us. This is already given to us. So WADB. Now what is WADB? See, WADB is actually dependent upon two processes which are shown here. One is this particular process AD and other is BD. Okay, there are two processes. So what we can do, we can calculate the total work by adding these two processes, work of these two processes. Now you tell me, if I talk about the process D to B, what is this process? Can you tell me?
Constant volume.
Constant volume. So what is the value of W in this case?
0.
0. So it is 0. So this is 0. So that means it should be equal to WAD. So basically in this process, the work which was said to be done during the path ADB is actually equal to AD only. So which is equal to 10.5 only. Okay. So that means for the process AD, I have the value of work available with me. Okay. This is with me. So I can now what I can do is I can use this particular equation for the AD process. So QAD will be equal to UD minus UA plus WAD. Okay. So UD, the value of UD is given as 42. You can see it here. This value is 42 and UA is 0. So this is also given to me. And WAD, this WAD we have just calculated, it is 10.5. So the value of heat transfer this particular process comes out to be 52.5. So this is now known to me. Now I also have the value of total heat transfer for the process ADB which we calculated earlier. You can see it here. This is the value of ADB, QADB. This was equal to 62.5. So total ADB, this QADB will be equal to QAB AD plus QDB. Okay, so QAD is 52.5. This is there, and QDB is to be calculated, and this was equal to 62.5. So actually, QAD comes out to be 10 kilojoules. So this is how we can calculate it. Okay, is it clear? Okay, you can see it. Okay,
Yes,
now
sir.
let us see this numerical problem. Air is initially at 260 degrees Celsius. Initially at 260 and 700 kilopascal and occupies 0.028 meter cubes. The air is expanded at constant pressure to 0.084 meter cube. So let me stop here. Let me write some values here. Okay, now you see here actually. I have written the state point 1. I am given with the temperature 260. So I write it here. Temperature is 260. Pressure is 700. So I write the pressure as 700 at state point 1. Then I write the volume 0.028. So it is given here. Okay. The air is expanded at constant pressure. So we are talking about state point 2 now. So at state point 2, the volume is 0.084 and it is the constant pressure process. So the value of pressure will be same 700. So now I am left with this value, and this value. So it is basically T2 if you see here, V3 and P3. These are the three unknown values which are not known to me. Now let us read the question further. A polytropic process with n is equal to 1.5 is then carried out. So after the constant pressure process, it is the polytropic process which is following. So I have written it here. Process 1 to 2 is constant pressure. So P1 is equal to P2. Process 2 to 3 is polytropic, which is PV raised to power 1.5 is equal to constant. Okay. And then followed by a constant temperature process which completes the cycle. So it's the system is air is the system here. Thermodynamic system is air, which is undergoing a cycle actually. So the third process is process 3 to 1 in during which the temperature is constant. That means T3 is equal to T1. So it means that is why if you see here, I have written the value of T1 as 260 and T3 also I have written as 260. That is the reason why the value of T3 is 260 because the temperature is constant. Okay, I hope the question is clear. And here I have drawn the PV diagram showing the first process only 1 to 2. It is the constant pressure process and the volume is changing from V1 to V2, and these are the values of V1 and V2. So it's a horizontal straight line here. Okay. Now let us read the question further. All the processes are quasi-static. That means reversible. Consider the air is in a expanding in a piston cylinder device. So that means we are saying that it is a closed system. Okay, closed system. Find pressure, temperature, volume at all salient points of the cycle. Calculate W, Q, and delta U for each process. Sketch the cycle on a PV diagram. Okay, so we have to calculate the missing parameters. Which missing parameters? I have just told you this is missing, T2 is missing, V3 is missing, and P3 is missing. This is what I have to calculate actually, and then for each of the process 1 to 2, 2 to 3, 3 to 1, we have to calculate the value of heat transfer, work transfer, and change in internal energy. This is what is asked to us, and then finally it has been said sketch the cycle on the PV diagram. So we have to sketch the cycle on the PV diagram also. So this is the question. Okay. Right now we have 8-9 minutes. So let us see. Now, once again, I have given this state point information in this slide also. And I know that the first process is constant pressure process. And for the constant pressure process, we have this particular relationship between the volume and temperatures. So V1 by T1 is equal to V2 by T2. So if you see the diagram, if you see the table here, I have mostly all the values. I know the value of V1, I know the value of V2, I know the value of T1, but T2 is unknown. So naturally, I can calculate the value of T2 from this equation. But mind it, I have to keep this value of temperature in Kelvin actually. So I have added 273 to 263. Okay, and then I have put the values of volume, and I can see this is the value of the T2 temperature. So what I can do, I can write it in the table. So I have written it here. T2 1599.45. Other values are as it is, and still we are have two unknowns here. Okay. Then the third process, second process is polytropic process given by PV raised to power 1.5 is equal to constant. So now I have to calculate P3 and V3. This we have calculated 1599.45. Okay. Now if you use this particular equation, which is P2 V2 raised to power n is equal to P3 V2 raised to power n. Okay. We cannot calculate P3 nor V3 because these two values are not available to us. So this is not available, this is not available. So you won't be able to calculate either P3 or V3 from this equation actually. So what should we use? We should use other two relationships. One relationship is TV raised to power n minus 1 is equal to constant, and another relationship is P by T raised to power n over n minus 1 is equal to constant. Now you just try to understand it. Just try to write this equation for the process 2 to 3. So you can see T2 V2 raised to power n minus 1 is equal to T3 V3 raised to power n minus 1. Now you see in the chart here. You see the chart here. So are we available with T2? Yes, T2 is available to me. Am I available with T3? Yes, I am available with T3. Am I available with V2? Yes, V2 is available to me. What about V3? V3 is unknown. Okay, so simple. I can calculate it from here. So you just have to put the values here, and the value of V3 comes out to be 0.756 meter cube. Now let us go to the next relationship. Now P by T raised to power n over n minus 1 is equal to constant. So am I having P2? Yes, I have P2 here, 700. Do I have P3? This value? No, I don't have this value P3. Okay. Do I have T2? Yes, I have T2, which is 1599. Do I have T3? Yes, I have T3, which is 260 degrees Celsius. So put these values and get the value of P3, which is actually equal to 25.93. So this completes my table. So this is the complete table which I have drawn here. Okay. So this is how I can calculate the values. But my advice to you is, though here you are just seeing this numerical problem, until you solve this yourself, you will not be acclimatizing what are the problems when you are solving the numerical problem. Okay, so you have to solve it in your hand on a notebook. Don't think that I am teaching you here, because you can see I have also done it. If I will be start doing it mentally, I also won't be able to do it. So it's better that you also solve it yourself. Okay, let us proceed further. Now this, all these values are given to me. Okay, now what is the value of p1? 700. So this is 700, and the value of this is, I am drawing PV diagram, pressure and volume diagram. Volume is also known to me, so I can say that this is 0.28. So this point can be located easily. Process 1 to 2 was constant pressure process. So 1 to 2 is pressure is equal to constant. 2 to 3 is PV raised to power n is equal to constant. 3 to 1 is temperature is equal to constant. Okay. So now at 2 I know the pressure. At 2 I know the temperature. Sorry, volume. Okay. Pressure is known and the volume is known at 2. So I can locate this point 2. Okay. This point, just a minute. This point can be located easily. So process 1 to 2 is easy to understand. Now let us go for the point number 3. Once again, it's a pressure volume diagram. So pressure is known to me and the volume is also known to me. So you can see this pressure is lower, whereas the volume is higher. So that means this point will lie somewhere here. This is 25.93 and this is 0.756. So I can locate it. Now, once I locate it, what is the last process? Last process, you know, is constant temperature. So you just have to join point number 3 with the point number 1, because at 1 and 3, the temperature is same. So this process automatically is constant temperature process once you have calculated all the values. Okay, now my advice to you is, I have calculated, I have drawn this diagram. After I have got these values. Okay, what you try to think is, suppose you have you don't have all these information, whatever the values you have calculated, just think, if you are asked to, if you have these three processes and you have to draw this PV diagram for the whole cycle, whether you are able to draw it without calculating the values or not. If you can, then you have understood. You can draw it without calculating the values also, mind it. Okay, it's not necessary that you calculate the values. You can always draw this diagram without calculating the values also, and that you can do. So give a try to it. Okay, next everything is very simple. We know about the processes, we know about the various equations. You know, if it is a constant pressure process, how you calculate the work. This is the equation of the work. All the values are known to you. You can calculate the work. The temperatures are known to you. You can calculate U2 minus U1. Yes, only thing is you need to know the value of CV, which is 0.718. This is the value for air actually. And you should remember it. Nobody is going to tell it to you in the examination. If it is not given, you have to remember it. But yes, we are not given with the value of M. So how to calculate M? M can be calculated from this equation. And these are the parameters which you need to remember for the air, because air is a substance which will remain throughout your life. You are breathing air. Okay, so you know the value of R, CV and CP for air. And similarly, you should know the value of CP and CVR for water also. Okay, it doesn't matter. You will remember it slowly. So M can be calculated from this equation which comes out here. You can calculate once again change in internal energy. After calculating this, the value comes out to be this much, 98.17. You know the formula of change in internal energy. It is mCv T2 minus T1. Okay. So then you know, for any process you can use the first law of thermodynamics, and then you can calculate the value of Q1 to 2. Then you can go for the process 2 to 3. The work is given by P2 V2 minus P3 V3 over n minus 1. You put the values, calculate it. Then you can calculate change in internal energy once again. This comes out to be this value. Then calculate heat transfer. This can be calculated easily from the first law of thermodynamics. This is FLT. Okay. Then go for the process 3 to 1, constant temperature. Change in internal energy will be U1 minus U3 will be 0, because temperature is constant. This is written here. Okay. W and Q are same. So this is the value formula for the work, and then this is the value of work, and same will be the value of the heat transfer. Okay, this is what I wanted to explain you, but my advice to you is you solve this numerical problem yourself and it will raise your confidence level. Okay, so just wait, I will take your attendance.